Hi, I'm Will Bushy, and this is the second lab presentation for physics, and this one is modeling gravity and projectile motion. So the purpose of this lab was to demonstrate the force of gravity, which is the gravitational constant times the mass of the larger object times the mass of the smaller object divided by the distance between them squared times the unit vector. The coded model shows a net force and acceleration solely due to gravity on the object, whereas the real-life test was compounded by factors such as air resistance and other outside errors, making the acceleration smaller and thus the descent slower. When drag is introduced to the computational model, the acceleration downwards is greatly decreased and almost reaches a constant velocity. As you see here was a paper filter dropping from a height of 1.5 meters. So the equations used in this lab were as follows. The coded model uses g equals negative 9.81 meters per second squared as acceleration, and the resulting equation is the change in the position for y is the initial velocity times time plus gravity times time squared divided by 2. In this case, the initial velocity is 0, so time is 2 dy over g to the 0.5. This model predicted that it would take only 0.7 seconds to reach the bottom of the 1.5 meter drop, and if it were allowed to fall for the entire 1.767 seconds that the experiment took, it would reach a position of negative 1.73 meters, so a total displacement of 18.8 meters in magnitude. In reality, the drag affected the projectile and it took 1.767 seconds to complete the fall. The paper filter was dropped from a height of 1.5 meters and the initial velocity was 0, 0, 0. As you can see on the graph, with the blue representing the actual model, which was a much slower descent, and the orange representing the purely theoretical model and idealized conditions, the computer said that the rate of fall would be increasing much faster. And the gray dots represent when drag is introduced into the system. In this case, it was b equals negative 3. It was a much slower rate of fall than the other theoretical model, and it almost approached a constant velocity towards the end. So coding here, you had to set your initial y position as 1.5 meters above the x-axis, and everything else was in the 0 position, and the vector for velocity was 0, 0, 0. Time would be taken each 0.1 seconds, and the equations updated to update acceleration, position, and velocity, and g was 9.8. So while t was less than 1.8 seconds, roughly the time it took to fall, the net force would only be in the y direction, and it would be the force due to gravity plus the force due to drag. And in the original theoretical model, that was equal to 0, so it was just solely gravity causing the object to fall. Then you take the force net, which in this case is just the acceleration because we're using mass equals 1, times the delta t, the change in time over the interval. And so it would be the initial velocity plus acceleration times time would be your final velocity, and position would be a similar equation. So possible sources of error in this experiment were the presence of air conditioners and fans in the room may have further buoyed the filter. The height might have been incorrectly measured of the drop, so it might not have been exactly 1.5 meters, and the exact angle of filming relative to the motion of the object could have caused data distortions in Tracker. So what does this mean? This means that the theoretical models will always have the object falling faster than observed. When drag is accounted for in the computed model, the velocity approaches a plateau, meaning gravity and drag are in equilibrium, so the net force is 0. If the object were initially thrown down, it would have a faster rate of descent, then level off somewhat as drag would act more quickly on the object, and thus the net force would be 0. Thank you.